Okay, I'm going to be discussing linear models. But however, before I do that, I want to alert to everybody the fact that the next door class has a class, the next door classroom has a class going on. You may hear noise from there coming in here, but this is the only classroom I could find open at this particular time. So I'm going to start, we are going to be going for linear models of this form. But before I can do that, I need to review the distributive property and apply some and do some tricks with it. Okay? So if you have some number multiplied by two numbers being added or subtracted, you can take this number times the first times this number times the second. So example 1. 5 times x minus 3. Well, 5 times x is 5 times x, because you don't know what it is. Let me make that a plus. 5 times x plus 3. So 5 times x is 5 times x, and 5 times 3 is 15. Okay, now, sometimes variables are used. Variables are letters that represent numbers. So this x represents a number. Quite often, it represents a specific unknown number. Other times, it represents any number. It allows us to generalize the relationships between numbers. So, if x equals 1, I have 5 times 1 plus 3 equals 5 times 1 plus 15. That's 5 times 4. That's 5 plus 15. And 20 equals 20. Okay? If x equals 2, I have 5 times 2 plus 3 equals 5 times 2 plus 15. So that's 5 times 5. That's 10 plus 15. And 25 equals 25. Okay? So that's one of the purposes of using letters to represent numbers. We're, in this particular context, in this particular meaning of a variable, we're saying that it doesn't matter what x is, this will always equal that, regardless of what number we have here. Okay? So here's the second example. Example 2. 3 times x minus 4. Well, 3 times x is 3 times x. And 3 times minus 4 is minus 12. Example 3. 10, or we'll do 10. Negative 10. Negative 10 times x plus 8. Well, negative 10 times x is negative 10x, and negative 10 times a is negative 80. Negative 10 times a is negative 80, which we'll treat as minus 80. Example 4. Negative 2 times x plus 1 would be negative 2 times x, and negative 2 times 1 is going to be minus 2. And example 5. Negative 6 times x minus 4. I've already used that number. Let's do 7. So minus 6 times x will be minus 6 times x. And negative 6 times, so minus 6 times minus 7, minus 6 times minus 7 is plus 42. Okay? You try. I'll give you about 30 seconds to try this yourself, and then I'll put the answer on the board afterward. Okay, I didn't like the first one I just was about to use, so here's that one. Try that one. I'll give you about 30 seconds. 8 times x is 8x, and 8 times 2 is 16. Okay, so that was the first preliminary. Next one, solve for y. So example, y minus 4 equals 11 times x plus 3. First, you always multiply. So first multiply. So I'm going to leave this alone. 11 times x is 11x, and 11 times 3 is 33. After you have done both multiplications, so let me re-clarify this. Both multiplications. Second, isolate y. Undo add by subtracting. Undo subtract by adding. Okay, so I would undo this subtraction of 4 by adding 4. Now, if I add 4 to this number, I will add 4 to this number, which doesn't have a variable. Okay? If you don't have, if it doesn't have a variable, it can only be added to another number with no variable. So this will give me y equals 11x plus 37. Here's another example. Y plus 2 equals 10 times x minus 4. So first, I do the multiplications that have to be done. So that's going to be 10x, and 10 times minus 4 is minus 40. So I've done both the multiplications. Now I'm ready to subtract the 2. I would undo addition by subtracting. Okay, now think of this as gains and losses. I've already have a negative number represents a loss. And so I'm down 40 already, and I take 2 more away. That's minus 42. Okay? Here's another example. Y minus 3 equals 8 times x minus 2. So y minus 3 is going to be left alone. That's 8 times x, and 8 times minus 2 is minus 16. I will undo this subtraction by adding. The 8x is left alone. This is a loss of 16, but we gain 3. A loss of 16 with a gain of 3 is a net loss of 13. Okay, in the interest of making sure we can actually see it, I'm going to represent the U try. So U try y plus 1 equals 6 times x plus 4. I will give you about 1 minute to try it. Giving you a minute to try it. All right. So I go ahead and do both of those multiplications, and I subtract 1. So y equals 6x plus 23. All right. I'm going to pause here and put up the next part of this. Okay, so for the main event, linear models. All right, these are formulas of this form that are designed to hit certain data points or approach certain data points. Okay, or in an actual XY plane that you might have seen in algebra actually hit geometric points. Okay, but in this case, what we're going for is we're actually going to try to apply these. So what I'm going to be showing you is linear equations primarily for application, but as a transition step, I'm going to give you the algebra you might have seen before. All right, so this is y equals slope times x plus the y-intercept. That is typically called the slope. It's the rate of change. And the formula usually given is what m equals y sub 2 minus y sub 1 over x sub 2 minus x sub 1. And this is the intercept, the y-intercept. Also just called the intercept. Okay, I think I'm just going to call it the intercept this time. Okay, for an applied problem, that's usually what is referred to by the intercept. Okay, and it is the value of y at x equals 0, and it's also considered the start value. In an applied problem, it's typically thought of as a starting value. So let me give you an illustration. Sometimes y minus y sub 1 equals m times x minus x sub 1 is used as a preliminary to that, okay, where these represent coordinates. Okay, so illustration. So this is what you might have done in an algebra class at one time. All right. So this represented x, this represented y. I'm going to make it simple. 1, 2, 3, 4. Negative 1, negative 2, negative 3. 1, 2, 3, and 4, and 5. Negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, and negative 7. So this point will be 2, 1. This point will be 3, 5. All right? Find equation of line through 2, 1 and 3, 5. 2, 1, 3, 5. Okay, so here's what you might have done in algebra. Do m equals y sub 2 minus y sub 1 over x sub 2 minus x sub 1, as stated here. Okay? Now, it's always x, y, x, y. X coordinate, y coordinate, x coordinate, y coordinate. So I would take the second y minus the first y over the second x minus the first x. That gave me 4 over 1, which was 4. Next, I would use this. And I'll go ahead and use this point. You could actually use either of them, but I'll use this one. I choose 2, 1, because technically it represented the x sub 1, y sub 1 in the slope formula. So y minus the y coordinate 1 equals, the slope was 4, x minus the 2. So, like we did before, we do the multiplications. 4 times x and 4 times minus 2 is minus 8. Next, I want to get the y by its lonesome. I undo the subtraction by adding 1. And y equals 4x minus, a loss of 8, gain 1 is a net loss of 7. Okay? So if I was to draw this line, it would go through these points. Okay, if I was a better artist, that's what this would be. Okay, I don't have a straight edge, and I couldn't find a yardstick, so this is the best I can do. I don't have a straight edge this large. So that's the best I can do. If you notice, these points are over 1 and up 4. Okay, that's what this slope represented. Y went up 4 for every 1 unit of x. Y went up 4 for every 1 unit of x. Hence the rate of change of y per unit of x. Okay, but this isn't exactly the type of problems you're going to be doing in a quantitative reasoning course. So let me give you the type of problem you will do, you might do. Example, a person is paid a flat rate for a minimum 3-hour shift. Okay? Then, if he stays to work X optional hours, he is paid hourly. Create a linear model for pay y, based on x optional hours. Okay? So here's a table. All right, I'm going to set this up as I go. Total hours. Optional hours. Total pay. Y. So optional hours X. I'm going to put some space in there. Optional hours X. And total pay Y. Okay, now, after working 5 total hours, total pay is $82. After 7 total hours, pardon me. After 7 total hours, it's $104. And after 10 total hours, actually, let me make this 11 total hours to avoid confusion later. It's $148. Okay. Now, I'm not basing my model on how many total hours are paid. I'm interested in a linear model based on X optional hours. So since this includes a 3-hour minimum shift, that leaves 2 optional hours. This leaves 4 optional hours, and this means 8 optional hours. Okay? So this isn't going to be part of the linear model question. Okay? Sometimes you need to know when to filter out extraneous information once you got what you need. Because remember, the model is going to be based on X optional hours, not total hours. And the total hours includes this minimum 3-hour shift. So from here, we're going to create a linear model. Then answer questions. So I'll have questions to ask after we do this. Okay, so do. The points are 2, 82, 4, 104, and 8, 148. I teach my students to use the first and the last. Okay? So if you've got 4, you still use the first and the last. Okay? That's what I do. I teach my students to use the first and the last. So M will equal y sub 2 minus y sub 1 over x sub 2 minus x sub 1. So that would be second y that I'm using minus the first y I'm using over the second x I'm using minus the first x I'm using. So 148 minus 82, 66. Divided by 6, that's 11. Okay, so my slope is 11. Y minus y sub 1 equals m times x minus x sub 1. And I choose 282. Okay, 282. So that'd be y minus the 82, that's the y coordinate in this context, equals the slope 11 times x minus the 2, the x coordinate. So y minus 82 equals 11 times x times 11 times minus 2. That's negative 22. The next thing I need to do is add 82. So y equals 11x, and if I'm down 22 and I gain 82, down 22, gain 82, that's a net gain of 60. So that's 11x plus 60. Question number 1. What is rate of change? Question, what is rate of change? Question number 1, what is the rate of change? Well, as a strict number, it's just 11. But we're going to want more in a quantitative reasoning class. What does that number mean? Okay, well, y represents dollars, x represents your optional hours of work. So it represents $11 per 1 hour. So $11 per hour. That is what that means. $11 per every 1 unit of x, which are hours. Okay? Question number 2. What is hourly pay? Answer, $11 an hour. Okay? So after the person has worked their minimum 3-hour shift, the pay is $11 an hour for however late they stay to work. Okay? But I got more. I got another question I want answered. So I'll squeeze it in over here. Question number 3. What if he worked no optional hours? What if he worked no optional hours? Do. Y, this means x equals 0. So y equals 11 times 0 plus 60. Okay, so 0 plus 60 is $60. So I'm going to reword this as rate of change with a question mark. Okay. Question number 4. What is pay for minimum shift? I actually already answered that. Okay, if the person immediately leaves after their shift, it's the start value, $60. Okay, so once they've done their minimum shift and are moving on to the second phase of their workday, once they have done their minimum shift, Once they're on to the second phase of their workday, the hourly pay, they've already got 60 bucks that they're starting out with. Okay, and then the 11 bucks per hour is going to be on top of that. Okay, to make room, I'm going to have to erase all of these. I got a couple more I want to answer. Question number 5. Pay for, or what is pay for? What is pay for? Or how about, what is pay for 13 total hours? What is pay for 13 total hours? Do. 13 total hours includes those three mandatory hours. So that means X equals 10 optional hours. Okay, that means 10 optional hours. So I'll plug in 10. So 11 times 10 plus 60, that's 110 plus 60. That gives me $170. All right. Question number 6. How many optional hours are needed to get 200? Round to nearest hour. Okay? How many hours are needed to get $200? Okay, do. In this case, the total pay, I want the total pay to be 200. Okay, most students are not comfortable with having the X on the right side. Their students oftentimes want it on the left where they're used to seeing it. So that's where I'll put it. Now, what's going on here is X is being multiplied by 11 and then 60 is added. The result is 200. So I'm going to reverse this. If X was multiplied by 11 and then 60 was added, I will subtract the 60 and then divide. So 11x equals 140. Next, I will divide by 11. Okay? So 140 divided by 11, x equals 12.7 with the 7 2 repeating, and it says round to the nearest hour. So that amounts to 13 hours. Okay? The person will need to stay and work 13 hours to get $200. Okay, so that was actually a more complicated example than this one. What I wanted to do is I wanted to link the graphical type problem that I did earlier with an application type problem. But in many cases, you're not going to have to find the rate of change. Sometimes everything you need is in the word problem. Okay, so here's one. A technician charges 40 bucks for the first hour. That's called the initial hour, their first hour. After that, he charges $35 an hour for additional hours. Create a linear model for capital L being labor costs and H being the additional hours. Okay, so the premise of this problem is where I'm from, a house call is usually considered an hour or less. So they'll charge so much for a house call, and then if they have to stay longer, they'll start charging you an hourly rate on top of the house call bill. So from this person, you're definitely going to be charged 40 bucks. Plus, now, if the person stays an additional hour, that's $35 one time. If they stay for 2 hours, that's 35 bucks 2 times. Okay, and if they stay for 3 hours, that's 35 bucks 3 times, and so on. So it's going to be $35 times the additional hours. But that's represented by H. So L equals 40 plus 35 times H, which would normally be written with the variable first, so 35H plus 40. Please note that math is case sensitive. That is correct. This is not. No. Okay? Here's another no. Lowercase l equals 35h plus 40. Also a no. Okay? Use the correct case. Okay? This is the correct version. Uppercase L should be represented by uppercase L. Lowercase h should be represented by lowercase h. Okay, lowercase h should be represented by lowercase h. Okay? Make sure that not only do you have the right letter, you have the appropriate case. All right, well, I'm going to stop here.